These notes are on ellipses. So in class, you did an activity in which you had a piece of string where you put the endpoints of the piece of string in two different locations and then used your pencil to trace out the string where the string length didn't change. So the definition, and that gave you a nice oval shape, which we call an ellipse. So the definition of an ellipse is the set of all points, x comma y, in a plane, which have the same total distance from two fixed points called the foci. So the place where you put the endpoints of the string, those are each the foci, and the same total distance means that that string length didn't change as you use your pencil to trace it out. So in standard form, we have a number of pieces of information given for the ellipse, for graphing an ellipse. We have the center, and then we have the distance along the x-axis and the y-axis, and we also can find the focus from that. I'll note here, when I have written, so up here I have the a squared and the b squared. The a squared simply is associated in this case with the x value, and the b squared is associated with the y value. In the equation for our foci, it should be noted that only in this case, a must, the a squared must be bigger than b squared. So we're going to look at an example in which the bigger number is underneath the x value, and then another example where the bigger number is underneath the y value. This is just, instead of having two separate forms, standard forms for the ellipse, I'm going to have one, and I just want you to note that regardless of what numbers sit under here, when you're looking at finding the foci, you have to make sure that the bigger number is what sits on the left-hand side of the formula for the Pythagorean theorem. So let's look at this first example. In this first example, my center is 0, 0. And the number underneath my x term of this equation tells me how much left right to go. So from my center, I go the square root of 25. So 5 to the right, 5 to the left. The number underneath my y portion of my equation tells me how much up, down to go. So in this case, the square root of 9, which is up 3 and down 3. And now I have the longest length of my ellipse and the shortest length of my ellipse and the longest, which means I connect these 4 points in a sort of long circular shape, that ellipse shape. And the longest length, keep messing that up, the longest length has a special name, and the shortest length has a special name. The longest length in this ellipse is along the horizontal, and that longest side is called the major axis. The shortest length, which for this hyperbola is along the vertical, or the y-axis, is called the minor axis. Now, not all ellipses are long horizontal. Some are long vertical. And so it's just a matter of looking at which is the longest, which is the shorter, and labeling the minor and major accordingly. So the last thing I want to do is to find the foci, because in an ellipse, the foci are what give us the general shape. It's almost as if the ellipse has 3 centers, quote unquote. It has the place where I start in order to graph my major and minor axes, but it also has those 2 points that actually form the ellipse. Again, like you saw in class with the string and the endpoints of the string being in 2 different locations. Those are the foci. So I'm going to use my equation up here. A squared equals b squared plus c squared, where a is the bigger of these 2 numbers. So that's going to be 25 equals 9 plus c squared. Subtract 9 on both sides, and I get 16 equals c squared. I get c equals 4. So that means that from the center along the major axis, I go 4 units to the right. So there's one foci, and 4 units to the left. There's my other foci. So the address of these two is over 4, 0, and over negative 4, 0. Let's look at a second example. In this case, the example we're going to look at does not have the center at 0, 0, so definitely making it a little bit more complicated. However, the nice thing about all of this is it's very visual when you're graphing it. So I use the same exact process. I first find my center, which is 5, negative 2, so 5, negative 2. And then from there, I do exactly what it tells me in terms of how much left-right to go and how much up-down to go. In this case, my left-right is 2 because that's the square root of 4. So left-right 2, left 2. And my up-down is 6 because that's the square root of 36. So up 6 and down 6. 1, 2, 3, 4, 5, 6. There we go. And then I connect those 4 points, to make my elliptical pattern, elliptical shape. And again, my ellipses don't always come out so beautiful. The important thing here is that your teacher can see where these 4 points are and that you've connected them to make an elliptical shape. Again, if I'm looking at this, in this case, my major axis, my long axis, is actually along the vertical. And my minor axis is along the horizontal. It just depends whether or not the bigger number is underneath the x portion of the equation or the y portion of the equation. And now I also want to find my foci. So remember, my equation for my foci here is this, but my a squared is always the bigger of these two numbers. So I have 36 equals 4 plus c squared, 32 equals c squared, square root of 32 equals c, so c equals 4 root 2, or approximately, this will be important so that I can actually graph this, approximately 5.66. So from the center, along the major axis, I'm going to go up 5.66, so that's 2, 3, 4, 5, right there, and down 5.66, right about there, F2. And now if I want to write the actual location of these, remember that I'm actually trying to find this exact point, which means that I've gone over 5 and then up so much and down so much. So my foci are going to be, I went over 5, and then because this is a square root and I can't just count, I have to actually use my center as my reference. So I went over 5 and down to negative 2, and then I went up 4 root 2, and I also went down 4 root 2. Those would be the exact values of my foci. If I wanted to find the approximate values, I would have to use my calculator. So I would negative 2 plus 4 root 2, which is approximately 3.66, and 5 comma negative 2 minus 4 root 2, which is approximately negative 7.66. And we can actually see that here if we're counting. We would have gone up 1, 2, 3, and then another 0.6, and here we would have gone down 7 and then another 0.66. Another topic that you explored when you were looking at ellipses were transforming the equation of an ellipse from expanded form to standard form. And for this process, you have to use completing the square, just as you did when you were going from standard form to vertex form for parabolas. So the first thing I'm going to do is I'm going to group my x's together and group my y's together. I am then going to make sure that the coefficient for my x's is 1, so I'm going to factor out my 2 in front of my x squared, and then the same thing for my y's, but in this case my y's don't have a coefficient, so I leave them as is. I also am going to leave a space with my x's and my y's in order to do the process of completing the square. Completing the square, I take my b value, divide it by 2, and square it, so that's 9. But remember, what I've actually added to the left-hand side of this equation is 2 times 9. So I need to add that to the right-hand side also. For my y portion, I take my b value, divide it by 2, and square it. So I'm adding 4. This time, I'm adding 1 times 4, so that's just 4. I then write my perfect square trinomials as perfect square binomials. And I simplify my right-hand side. So 36 plus 4 plus 18 is going to be 58. And my last step with writing the equation of an ellipse in standard form is that my equation has to equal 1. So I divide everything by 58. So divide this by 58, this by 58, and this by 58. In my first portion here, I want to get rid of the 2 in the numerator, and so I reduce this fraction. So I end up with x plus 3 quantity squared all over, oh god, what's 58 divided by 2? Making sure I get this exactly right. There we go, 29, I should know that. Plus the y plus 2 quantity squared all over 58. There was no number in front, no coefficient in front of my perfect square binomial to reduce the 58. Equals 1. And now I have transformed the equation of this ellipse from expanded form to standard form. Let's look at a second example using that same process. In this case, we've made it a little bit more difficult because now I have a coefficient in front of my x's and my y's. So again, I regroup my x's, regroup my y's, factor out the coefficient in front of my x's, and factor out the coefficient in front of my y's. Complete the square here, so that's plus 1, but really I've added 2 times 1, so plus 2. Complete my square here, so that's plus 4, but I've really added 3 times 4, so that's plus 12. I then rewrite my terms here as perfect square binomials. Whoops, typo. This should be, of course, minus 2 because my middle term in my y portion of my equation is a minus 4y. Equals 22 plus 2 plus 12 is 36. And again, my last step is to get my equation equal to 1, so I divide everything by 36. I can reduce this fraction so that I have x plus 1 squared all over 18 plus y minus 2 squared all over 12. 2 goes into 38 18 times. 2 goes into 36 18 times. 3 goes into 36 12 times equals 1. So the last thing that you may or may not have done with your teacher was to graph the ellipses using your graphing calculator. Now you'll remember that when you go to your graphing calculator and you go to the y equals screen, clear out that equation, that the graphing calculator does this by saying y equals, which means that if I'm going to input this equation into my graphing calculator, I actually have to have it where I'm solved for y. So the first thing I need to do here is to solve for y. So I'm going to move my x squared over 25 term over. So I have y squared over 9 equals 1 minus x squared over 25. I am then going to multiply the entire equation by 9. I have y squared equals 9 minus 9 times x squared over 25. And then I'm going to take the square root of both sides. Now remember, when you've taken the square root of both sides, you have some absolute value things coming up. So it's actually going to be plus or minus the square root of 9 minus 9x squared over 25. So in order to put this into my calculator, I actually have to put in two separate equations. I have to put in the plus the square root business and then a second equation with the minus the square root business. So I have the square root of 9 minus, and I'm going to use I'm actually not going to use some parentheses here. I probably will do that for the next section with the hyperbolas. But 9 minus 9x squared divided by 25. And then I press enter. And then I enter that exact same thing, but with a minus, a negative sign in the front. So square root of 9 minus 9x squared divided by 25. And then I press graph. And my last step here is that I may have to adjust my window depending upon, you know, whether or not my ellipse shows up fully. And there it is. I have a top branch and a bottom branch. You'll notice that along the x-axis is something kind of funny happens at this end. It kind of looks, on this side, a little flat, and this side it looks like there's a gap. That's just the pixels with the graphing calculator. So it may look a little funny, but that is the shape it should look like when you've got it graphed correctly.